Hello everyone, my name is Adin VS and our paper Acoustic Side Attack for Device Identification using Deep Learning Models is entitled with the paper ID number 2108. So without much further introduction, let us give an overview about the paper and the work we had done. So I hope you all are familiar with the terminology side channel attacks, which are passive attacks and can be used to decode device operations. So whenever there's the data processing or a computational work going on a computational device, probably there will be some sort of side channel leaks. So it is mainly or probably due to the weakness or fault in system implementation. So this side channel leak, it can be of various form: acoustic noises, electromagnetic interferences, power variation, etc. So these leaks are being captured and being fed to signal analyzers. So this signal analyzes this side channel leaks and extract the data out of it, and thereby having a data breach. So in our paper, we are making use of this acoustic side channel attack to identify a processor or a computational device based on the acoustic noise they have produced. So we got some number of devices, and using a quality microphone, we have gathered the acoustic noise data from these computational devices and categorized it into raw data sets. And after that, we have extracted the MFCC features from these raw data sets, giving us a preprocessed data set. And after that, we have fed these preprocessed data sets into classification models KNN, SVM, CNN, and LSTM. And of these all classification models, LSTM showed a better result with greater accuracy. So that was the overview part, and going for a short introduction. Is it possible to identify a device without seeing or accessing it? So because if you manage to identify a device, some devices have vulnerable software or vulnerable hardware component that can be easily exploited. For example, some of the routers or IoT devices, they use default credentials. So just by identifying the device, we could easily attack and exploit these devices. So we thought, can we identify the system specification just by analyzing the side channels? So that brought us into the question, is it possible to identify or classify devices based on their acoustic noise profile? So in order to gather this acoustic noise profile, we have created a recording setup environment. And in that environment, we have used a isolated or quiet environment with ventilation sealed rooms. And we have used a quality microphones with assist of a smartphone. And we ensured that the smartphone is at least 1 meter away from microphone in order to minimize maximum electromagnetic interference. And also we have turned the airplane mode on. And after that, as a part of recording configuration, we have executed a loop RSA encryption on every devices. So the purpose of RSA encryption is that the higher the workload, the more the Indian power varies. And as a result, noise will be produced. So it will be easier to gather this noise data. So any program was fine for this purpose, but for our comfortability, we have chosen looped RSA encryption on every devices. So similarly, we have recorded 1 minute samples and repeated it for 10 times. And finally, using a Linux command, we have split this audio into 5-second samples. And for configuration part, we have chosen the output file format to be .wav file format with a 48 kilohertz sample rate and mono channel type with frequency response of 22 kilohertz at 16-bit resolution. So these are the list of devices and its corresponding specification we have used in the project. Please have a look at it. Then our next step, data preprocessing. So we got our raw data set. Now we have to extract the MOCC features from these raw data sets. For this, as a first step, we have applied Hamming window to frame each of these signals. And after that, from each of these frame, we have obtained a frequency spectrum and applied MEL filter bank to each of these frequency spectra using the equation which is provided here. So here, according to the equation, the frequency is converted into, like the physical frequency is converted into MEL scale. And after that, we have computed the logarithm of all of these filter bank energies, and finally took a discrete cosine transform of these log filter bank energies, and finally it gave us the MWC features. So for this purpose, we have chosen the parameter sample rate is equal to 22050, FFT size as 2048 with a hop length 512, and number of MWC coefficient as 13. Then once the MWC features are extracted, we got our preprocessed data, and now we have to fetch this data into classification model. So we got KNN and SVM, which are machine learning classification model. In KNN, it is used to solve both classification and regression. And in case of support vector mission, it is an algorithm to find a hyperplane in an n-dimensional space that classifies the data points in a distinct way. So in case of KNN, the dataset is provided in CSV format, and of the dataset, we have split the dataset into in the ratio of 80:20, where 80% is used for training and 20 for testing purposes. And we have tested for k is equal to 3, 5, 7, 9, and 11. And with k is equal to 9, we have achieved a testing accuracy of 67.72% for KNN. And in case of SVM, the dataset is also provided in CSV format. This dataset is split in the ratio 70:20, where 70% is used for training and 20% is used for testing purposes. With the parameters, kernel is equal to linear, gamma is set to auto, and C, which is regularization parameter, as 2, we got a testing accuracy of 55.56% for SVM. Then going for CNN, which is a machine learning, deep learning classification model. In CNN, we have used 12 number of layers consisting of 3 convolution layers, a flattened, dense layer, and a softmax output layer. So here the shape varied from none 42, 11, 64 to none 10. So the dataset of the dataset, 20% was used for testing purposes, and 20% was used for validation purposes also. And finally, we have achieved a testing accuracy of 97.16%. And moving to LSTM, which is also a deep learning classification model, we have used 5 number of layers consisting of 2 LSTM layers, 1 dense layer, and an output layer. So here the shape varied from none 1364 to none 10. So of the data set, we have used 25% for testing size and 20% for validation size. And finally, we have achieved an accuracy, a testing accuracy of 99.6%. So these are the results that we have obtained. In table 3, we have provided a comparison between precision and recall values for different machine learning models in respect to the devices we have used in the project. And in table 4, we have also provided a summary of precision, recall, F1 score, and accuracy of different machine learning models also. So as a result, after this classification, LSTM has achieved an accuracy rate of 99.6%, followed by CNN with accuracy rate of 97.16%. And being a machine learning classification model, KNN has achieved an accuracy rate of 67.72% with k is equal to 9, and SVM has achieved an accuracy rate of 55.54%. So throughout the project, first we have created the data sets and extracted the MWC features from this. And after that, we have fed these features into classification models. And KNN and SVM has achieved a somewhat low accuracy as compared to LSTM and CNN. And in case of LSTM, it provides the best classification accuracy as it is good with larger data sets. And CNN also provided a better classification accuracy. So based on the model, we have successfully distinguished the devices using the audio samples. Then going for a future scope, primarily we can use this model for transfer learning. And then we can use it to identify processor specification. And also we can use to dictate false IC packages in devices by comparing it with legitimate acoustic signatures. So these are the references that we have used in the paper. Please have a look at it. And that was all about the presentation and project. Thank you for listening to our presentation.